And my intention is we have two portions. One is in two-dimensional, and then in two-dimensional we will talk about the using of the more circles. And then I want to introduce in general the thinking process for transformation in 3D in general. Okay, the 2D for the 2D, and that is we call the plane stress problems. Usually is like this. We have x, y, and for example we are given an arbitrary, for example the stress like this, tau x, y, and those ones are in equilibrium. And for 3D, these are three-dimensional stress elements, and then here we have is this x, y, z. So here in general we have all the stress components up here. And here is tau x, y. And again, for the symbols, here in general we describe the stress element is in matrix form. So here is sigma x, tau x, y, tau x, z. So this one indicating is, this one indicate is, the first symbol indicate is which plane these lines are. So this is called the x-plane. So this strain stress lies on the x-plane, pointing to y direction. So this is called the tau x-plane. So this is the direction. So very likely you can draw tau xz basically in the x-plane and pointing to z direction. So this is called the tau xz. Okay. So the first row indicating is the three stress components in the x-plane. Okay, that is the mathematical description of the stress components. Okay, so this is starting. And in the y plane, we have is normal stress, and then in the y plane pointing to x directions. So that is here. So this is tau y plane pointing to x direction. So tau yx. So this is tau y and tau yz. So yz in the y plane pointing to the z direction, yz. Okay. In the z plane we have sigma z. And in the z plane pointing to x direction, so this is tau zx. Okay. And this one pointing to y direction, so this one is tau zy. So in general, we utilize 9 stress components, and that in mathematics we describe in 3 by 3, the matrix form. And this one is symmetric. So that means these two components must be equal in magnitude. Okay, and tau yz equal to tau zy and tau xz equal to tau zx. Okay, so that is due to static equilibrium. For three-dimensional case, we have the general 9 components won't be 0. So for these situations, I'm going to hopefully I can show you the fundamental concepts how to do the transformation of the stress for this case. Okay, this is the most general, and this one we didn't talk about that one in mechanics material. And this is the spatial case of the 3D, and how can we define a plane stress? For this example, that means you can see is when under the situations, all the stress components pointing to z direction or any direction for this demonstration, for this illustration, I'm assuming z are 0. Okay, so that means as long as in your applications, if you can see in one direction all the stress components vanished, then that can be approximated as the plane stress, which means 2D. Okay, so that one, again, this is a huge application. For this case, is sigma z equal to 0, tau xz equal to 0, and tau yz equal to 0. Okay. And what kind of situation will fit into this category? And let me give you a few applications. First one is, say, if you would have the sheet metal. Okay, the sheet metal is a certain material like this. They usually have a very thin dimensions in one direction compared to the other. So for this one, the sheet metal, you can just safely approximate if you're going to use in your mathematical model or in the computer model, you can just use the sheet to approximate this one. And then I believe in all the software that would have the certain click option, plane stress. You click that one. You have to click that one, and then the computer will automatically accommodate appropriate change in modified material properties to accommodate for this case. Okay. Sheet metal or any film, any thin film like membrane. Okay, and those kind of situations you can just safely approximate using this one. So our starting point will be starting from here. Okay, so the more circles, let me give you a very quick review.